Hello, this presentation is for WASPAA 2023. I'm Shoichi Koyama from the National Institute of Informatics, Japan. The title of this presentation is Kernel Interpolation of Incident Sound Field in Region including Scattering Objects. Sound field estimation is aimed at estimating a continuous sound field inside the target region using multiple microphones. This task is a fundamental problem in audio signal processing, which has various applications. This kind of technique can be applied to spatial audio recording for VR audio, interpolation of acoustic transfer functions, active noise control in a spatial region, and so forth. A number of sound field estimation methods have been proposed so far. However, current sound field estimation methods have limitations. That is, the target region should not contain any scattering objects. This is because most of the current methods assume free space inside the target region. However, in some practical applications, an incident sound field in a region containing scattering objects needs to be estimated. For example, in spatial active noise control, the sound field inside the target control region needs to be estimated from microphone observations, but ANC users normally exist inside the target control region, and they can lead to scattering effects. So the degradation of estimation accuracy owing to scattering effects can become a significant issue. Our goal is sound field estimation in a region containing scattering objects of unknown properties. I mean, the shape of the objects and reflection properties on the surface are unknown. The sound field inside the target region omega containing scattering objects can be represented as a summation of the incident field and scattering field. We assume that one or more scattering objects exist inside the spherical region, omega SCT, within omega. We developed a sound field estimation method of the incident sound field, U inc, in the target region omega. From M microphone observations SM without prior knowledge of scattering properties. Our proposed method is a joint estimation of incident and scattering fields based on a representation of spherical wave function expansion. The incident field is represented by a weighted sum of kernel functions to constraint estimates to satisfy the homogeneous Helmholtz equation, which was previously proposed by the authors. Kappa is the kernel function and alpha is its weight. The weighted sum of the kernel functions at M microphone positions will approximate the incident field. We use the zeroth order spherical Bessel function for the kernel function, which corresponds to infinite dimensional spherical wave function expansion and guarantees the solution to satisfy the Helmholtz equation. On the other hand, the scattering field is represented by a spherical wave function expansion for the exterior field up to a truncation node n. Here, phi SCT is the spherical wave function for the exterior field, represented by the spherical Hankel function and spherical harmonic function. And nu and mu the order and degree of the spherical wave function. And USCT circle is the expansion coefficient. We approximate the scattering field USCT by the finite dimensional spherical wave function expansion, like this. We formulate the optimization problem to be solved like this. So in this formulation, we introduced matrix and vector representations of the observations, kernel weights, kernel functions, expansion coefficients, and spherical wave functions. So the first term is the squared error between the observations and the models of the incident and scattering fields. We also added the regularization terms like this. So this regularization term is the squared norm on the space defined by the kernel functions, and this term is the weighted squared norm for the expansion coefficients. And we define this weighting matrix W later. And this optimization problem has a closed form solution like this. So they can be derived by simply differentiating the cost function by alpha and U scatter circle and setting them to 0. Then the estimate of the incident field is obtained by using the estimated alpha like this. For the definition of the weighting matrix W, we assume the smoothness of the scattering field in the angular directions to alleviate dependence on the truncation order. Specifically, W is defined so that the regularization term for U SCT circle corresponds to the squared norm of the angular derivative of U SCT. Then the matrix W becomes this part. Since W consists of angular derivatives of the spherical wave function, so each element of W can be analytically obtained like this. So basically, this weighting matrix induces a small amplitude of high-order coefficients compared to the low-order coefficients. We show some results of the numerical experiments. We set the spherical target region in a free field, and 25 microphones are placed on the two spherical surfaces like this, and an acoustically rigid spherical object was placed at the center of the target region. A point source was at this position. The position is 2 meter, 2 meter, 0 meter. And we compared the method based on kernel ridge regression, KRR, which does not take into consideration the scattering effects, and the proposed method with or without the weighting matrix W. We also investigated two truncation orders, KR and 2KR. The evaluation measure was the normalized mean squared error of the incident field, defined like this. So please note that we only evaluate the incident field. So this plot is the NMSE of each method with respect to the frequency. So KLR does not perform well because it does not take into consideration the scattering effects. And low NMSE was achieved by the proposed methods, in particular using the weighting matrix W and the truncation order KL. So red one. The estimation accuracy of the proposed method without the weighting matrix W significantly degraded when the truncation order was 2KR. So the dependence on the truncation order was alleviated by the proposed weighting matrix W. And these are the estimated incident pressure and error distributions at 300 Hz. The upper figures are pressure distribution and the lower figures are error distribution. So as you can see, the estimation error was significantly reduced by considering the scattering effects. So let me conclude this talk. We proposed a sound field estimation method in a region including scattering objects. In some practical applications, the incident sound field needs to be estimated without prior knowledge of scattering properties. We modeled the incident and scattering fields by the weighted sum of kernel functions and circle wave function expansion, respectively. So we obtained the closed form solution for joint estimation of the weight of kernels and expansion coefficients. And we also proposed a weighting matrix for expansion coefficients to induce smoothness of the scattering field in angular directions. And high estimation accuracy was achieved by the proposed method below 600 Hz. The dependence on the truncation order was alleviated by the weighting matrix for expansion coefficients. So, thank you for your attention.